Ever wondered how the data packets travel seamlessly across networks? The secret lies in Ethernet technologies. Imagine the internet as a bustling city. The data packets are like the cars, buses, and bikes all traveling to different destinations. Now, imagine Ethernet technologies as the city's intricate road system, guiding those vehicles to their destinations without any hiccups. Ethernet technologies are the foundation of data communication, especially in local area networks or LANs. It's the protocol that allows your computer to talk to the printer or your game console to connect with the server halfway across the world, all in real time. When we talk about Ethernet, we're referring to a family of technologies. It's not just one thing, but a collection of standards and services that work together to ensure smooth and efficient data transmission. At its core, Ethernet is a protocol, a set of rules that dictate how data is formatted and transmitted over a network. Ethernet plays a pivotal role in ensuring that our digital world functions seamlessly. It's the unsung hero of our connected lives, working tirelessly behind the scenes to ensure that our emails reach their intended recipients, our social media updates get posted, and our streamed videos play without buffering. In simpler terms, think of Ethernet as the language of devices. Just as humans use languages to communicate, devices use Ethernet to talk to each other. Whether it's your laptop sending a print command to the printer or your smartphone connecting to the Wi-Fi, Ethernet is what makes it all possible. To understand how Ethernet works, it's essential to know its components and how they interact. Ethernet consists of a physical layer and a data link layer. The physical layer is all about hardware, cables, connectors, and switches. The data link layer, on the other hand, deals with how data is formatted for transmission and how access to the physical network is controlled. Now that we've grasped the basics of Ethernet technologies, it's time to delve deeper into the components that make it work. Ethernet technologies wouldn't function without some key players: hubs, switches, and routers. These are the pillars that uphold the vast digital networks we rely on every day. But what exactly are these devices? And how do they contribute to the smooth functioning of Ethernet technologies? Let's start with hubs. In the simplest terms, a hub is a device that connects multiple Ethernet devices together, making them act as a single network segment. It's like a big party line, where data coming in from one port is duplicated and sent out to all other ports. However, this can lead to data collisions and isn't very efficient, which is why hubs aren't used much in modern networks. Next up are switches. These are a step up from hubs. They also connect multiple devices, but instead of indiscriminately broadcasting data to all connected devices, switches are more discerning. They learn the physical addresses of the devices connected to them and send data only to the device for which it's intended. This reduces data collisions and enhances network efficiency. Lastly, we have routers. Routers are the maestros of network traffic, directing data along the most efficient paths from one network to another. They operate at a higher level than switches and hubs, using logical addresses or IP addresses to route data. Routers allow for communication between different networks, not just devices on the same network. So, in a nutshell, hubs indiscriminately broadcast data to all connected devices, switches selectively send data to specific devices on the same network, and routers direct data between different networks. Each of these devices plays a critical role in data transmission, and understanding their functions is key to grasping the intricacies of Ethernet technologies. With a clear understanding of hubs, switches, and routers, we can now explore more complex topics like the spanning tree protocol. Ever encountered a network loop and wondered how to prevent it? The spanning tree protocol, or STP, is the solution. As we delve into the world of networking, we come across various protocols designed to make our networks more efficient, reliable, and secure. One such protocol is the spanning tree protocol. But what is STP, and why is it so vital in our networks? Let's unravel this mystery. Imagine you're in a room full of interconnected doors. and you're trying to find the exit. The most efficient way would be if there was a single path leading you right to the exit. But what if there are multiple paths and you keep going round in circles? That's precisely what a network loop is, and it can cause a lot of chaos in a network. STP is like having a smart guide in that room who knows all the paths and can direct you to the exit using the most efficient path, while also blocking off all the other paths to prevent you from getting lost. This is the basic idea behind the spanning tree protocol. It prevents network loops by blocking redundant paths, and if the primary path fails, it unblocks a previously blocked path to maintain network connectivity. STP operates primarily in the data link layer of the OSI model, which deals with network topology and transfer of data between adjacent network nodes. It uses a specific algorithm to identify redundant links and block them, thus preventing network loops. This algorithm takes into consideration factors like path cost, bridge priority, and port priority to decide which paths to block and which to keep active. By controlling the network topology, STP ensures that data packets do not keep circulating in the network indefinitely, which can lead to network congestion and even failure. It maintains network stability by ensuring there is only one active path between network nodes at any given time. So, the spanning tree protocol is indeed a crucial tool in any network engineer's toolkit. It ensures our networks remain stable, efficient, and free from loops, thus maintaining smooth communication. Having understood what STP is, let's examine how it operates in real-world scenarios. Theory is one thing, but how does STP work in practice? Let's dive into some real-life scenarios to see how this protocol plays out. Imagine a large corporation with various interconnected networks. Each department has its own network, connected by switches. Now, without STP, if two or more paths between these switches are active at the same time, a loop can occur. This loop can lead to a broadcast storm, where data packets circulate endlessly, causing network congestion and potential system failure. But when STP is in place, it identifies these potential loops and blocks redundant paths, allowing only one active path at a time. If the active path fails, STP automatically unblocks a previously blocked path, ensuring the network remains functional. This dynamic nature of STP is crucial in maintaining network stability and efficiency. Another example is in a data center. Here, multiple servers and storage devices are interconnected for data, redundancy, and faster access. Again, without STP, multiple active paths could lead to data loops. But with STP, it ensures there's only one active path between devices, minimizing the risk of data corruption and loss. Lastly, consider a campus network with multiple buildings, each with its own network. These networks are interconnected, and again, the risk of loops is high. But STP comes to the rescue, identifying and blocking redundant paths, ensuring smooth data transmission across the campus. In all these situations, STP plays a critical role in maintaining network stability, preventing data loops, and ensuring efficient data transmission. It's like the traffic police of a network, directing data where to go, stopping it from going down the wrong path, and rerouting it when necessary. So, from corporate networks to data centers to campus networks, STP proves its worth. It's an unsung hero, working behind the scenes to keep our networks running smoothly and efficiently. These examples give us a clear picture of how STP functions, but let's not stop here. Ethernet technologies and STP are complex topics, but they're crucial for the smooth functioning of networks. We've come a long way in our understanding of these concepts today. Let's take a quick walk down memory lane and revisit the essentials we've covered. We started our journey with Ethernet technologies, diving into the heart of network communication. Ethernet, the most widely installed local area network technology, provides a smooth pathway for our data to travel. We explored its different types, understanding how each one contributes to the intricate dance of network communication. Next, we stepped into the world of hubs, switches, and routers, each a key player in the networking arena. Hubs, the simplest of the three, merely relay the messages they receive to all connected devices. Switches, a step up from hubs, smartly direct traffic only to the intended recipients, thereby reducing unnecessary network congestion. Routers, the most sophisticated, not only direct traffic within a network, but also connect different networks together, acting as a gateway. They're like the traffic police of the digital world, ensuring that data packets reach their destinations safely and efficiently. Then, we delved into the spanning tree protocol, or STP, a vital safety net that prevents looping in network systems. By creating a spanning tree that excludes potential loop paths, STP ensures data packets don't get stuck in an infinite loop, a situation that can bring a network to its knees. We also looked at some real-world examples demonstrating how STP can save the day in various network configurations. It's like the unsung hero of network engineering, quietly working behind the scenes to keep our networks stable and efficient. In conclusion, Ethernet technologies, hubs, switches, routers, and STP are more than just technical jargon. They form the backbone of our digital world, ensuring that our data travels seamlessly across networks. Understanding these concepts is not just about passing an exam, it's about appreciating the marvel of modern networking and the intricate systems that power our connected world. With this knowledge, you are now one step closer to becoming a network engineering pro. Stay curious and keep exploring.